Okay, that said, let me share the screen. There was something that I would like to say before we start with today's class. I mean, that's what discussed last time. We discussed a fractional threshold model in which basically you switch to the active state if a fraction of your neighbors are in the active state or larger. So in this case, for instance, we saw this example, actually two examples. This one, I'm not sure, I mean, I'm not doing it full screen now. You already seen this. I want to go quickly before then I share the slides of the final presentation. So you already seen this example in which a single active node managed to eventually to trigger a cascade that affected everybody. So that's remarkable. Of course, this is a small system. This is the same system, but instead of activating 1 as the initial seed of the process, we activate 7, and I showed you last time. It's the last thing I said, that in this case, with the same threshold, 1/2, sorry about that, you will not be able to influence everybody. However, and this is what some companies do, interested in viral marketing in general, also, and marketing departments of major corporations and so on, they try to unblock these cascades, to keep them going so that at the end, they achieve their goal of maximizing the influence diffusion. In this case, I don't know, the advertising of a product, propaganda, whatever message they're interested in spreading. And for instance, in this case, you can see that, I mean, of course, if you unblock 1, we've already seen that 1 alone is enough to convince everybody. But in this case, even if you manage somehow to activate 5 by targeted advertising or other strategies, once you activate 5, then it's easy to see that, 4 would have then 2 neighbors. One of them is active, which is half. And then 4 will be active. Because of that, 1 will be active, and then 2 and 3. So in this case, we unblock the cascade, which initially stopped at this point, and you can keep, can the influence keep going indefinitely? I mean, of course, this is a finite system. There could be other blockage. So knowing the structure of the network is very important. Knowing how the game works is important, because in this case, you can also act in a way to manipulate these cascades and maximize their impact. Okay, so that's the last thing I wanted to say about this, but of course, we're not done with influence spreading. I introduced then the sorry, this one. Threshold model, but today we'll start with independent cascade model, which is the other big class of models about influence spreading or information diffusion. So threshold models are based on peer pressure. Basically, you check how much pressure your neighbors, active neighbors in this case, are putting on you. The more people try to persuade you, the more likely it is that they will succeed. Social influence often works one-to-one, in pairwise interactions, because you may be persuaded by a single person. And that's the approach of the independent cascade models, in which interactions are binary. They are pairwise. They involve only pairs of neighbors and not one to many, like in the threshold models. So the idea is that each of our contacts has their own influence. And an independent cascade model works exactly like this. This is a sketch of the model dynamics. You have a bunch of probabilities. For each pair of neighbors, you have a probability Pij that node I, if active, if I is active and J is not, there is a probability Pij that I convinces its inactive neighbor J. And in general, Pij and Pji are different because not everybody is equally easy to convince. And what you do an iteration over all the nodes, and you consider all the active nodes in this case. And given an active node, you explore the inactive neighbors of each active nodes, and for each inactive neighbor, you have a probability Pij that I convinces J or influences J, And then you do the usual thing. You generate a random number between 0 and 1. You compare it to this probability. If it's smaller than this probability, then J is activated. Otherwise, it stays inactive. All inactive neighbors of I have one chance to be persuaded by I. So if I fails at this one-shot interaction, it will never be able to convince J again. This is, of course, simplifying assumption, because if you can keep trying, at some point you will manage to convince, and then you get the trivial results that everybody would be influenced, which is not, of course, what happens in reality. So this is an example of how it works. In this case, I emphasize the direction of the influence from the active nodes to their neighbors, inactive neighbors. So we start with node 1 being active. It has 4 neighbors, 5, 7, 3, and 2. Suppose that by doing this one-shot convincing attempt, 1 succeeds in convincing 5 and 2, but it fails at convincing 7 and 3. This is what you get in the second iteration. Now, 1 has already tried to convince all inactive neighbors. It succeeded twice. It failed also twice. So it activated 2 neighbors, but not the other 2. So 1 is out of the game. You cannot try to convince its inactive neighbors again. This is one of the rules of the model. But 2 and 5, which have been newly activated, they can try to persuade their inactive neighbors. So 5 can try to persuade 6, and 2 can try to persuade 3 and 8. Suppose that 5 fails at convincing 6, whereas 2 manages to convince 3, but not 8. So now, of course, 5, 1, and 2 are out of the game. I mean, they're active, but they cannot do anything anymore. But there is a new active node, which is 3, which has a chance to convince its only inactive node 4, and suppose that it does. So this is where the process stops. Unlike the threshold model, this is a stochastic process, which means if you can start from here and you take another sequence of random numbers, you are gonna generally find a different result. Because maybe in the next case, 5 and 7 will be convinced, and 3 and 2 will not be convinced, or all of them will be convinced. It really depends on the random number sequence. So that makes also the prediction and the preparations to this type of events kind of hard, because stochasticity can really change the results substantially. It does not only depend on the structure of the network, though, of course, that's critical. So the more active neighbors, of course, the more likely it is that the node will be activated. So it's similar in the sense of the threshold model. I mean, the principle is the underlying principle is similar, but of course, there are some key differences. Threshold models focus on the inactive nodes. You check each inactive nodes, and you check how much pressure the active neighbors put on the inactive node, and then you make your call. Whereas independent cascade models focus on the active ones. You take all the active ones, and for each of them, you consider all the inactive neighbors, and then you try to convince them one by one. And you have only one shot at doing that. Threshold models are also usually deterministic. It's a yes/no thing. Either if you are above the threshold, then the inactive node is activated, otherwise it stays inactive. Whereas independent cascade models are probabilistic, like I mentioned. They are stochastic because there is a probabilistic process of, like tossing a coin, being, of course, our random number between 0 and 1, comparing it with this persuasion probability. So it's more difficult to control a cascade in this case because you obtain many different scenarios for the very same network and for the very same choice of the influence probabilities. Now, of course, these models are very simple. I wanted just to give you the gist of this. I don't know how much you knew about these things. And people had a lot of fun trying to complicate them to make them more realistic. For instance, people have explored probabilistic versions of the threshold model because deterministic, versions are not so convincing. That's not the way it really works in society. There are always accidents, things that really can play out one way or the other, depending on the circumstances. And one way to do that is that the probability that an inactive node gets active can be set proportional to the number of active neighbors. So the more active neighbors that you have, the higher the chance that you're convinced. But it's talking about probability, like in the independence cascade model, no longer of a threshold that you have or not to surpass. So that would be a way to introduce stochasticity in threshold models. And And in this case, the neighbors would not accept influence independently of each other as in the threshold models because they kind of act together. But their collective actions, the effect of the collective action is to increase the chance that the node, the inactive node, is activated. And this naturally leads to the concept of complex contagion, in which each new person exposing us to an idea or product has greater influence than the previous ones, usually in a non-linear fashion. That's why it's called complex contagion as opposed to simple contagion, in which basically the influence is kind of linearly dependent. The influences of all the nodes are independent of each other. In this case, there is some sort of combination of the effects which lead to a result which is different from the nodes acting independently on the subject, the inactive subject. Okay, that's all I wanted to tell you within this course about information diffusion and or influence spreading. And we can move to the second class of dynamics on networks, which is perhaps the most popular one, also given what happened in the last few years with the COVID-19 pandemic, which is epidemic spreading. So you've seen already this map. I showed it to you on the first day about the potential applications of network science. This is actually very old. At the time, of course, there was no networks. There was not even science before. It was before Galileo. 13th century, but there was something really major happening those years, specifically between 1346 and 1353, the Black Death, the plague, which spread out to Europe, and it's estimated to have killed between 30 and 60% of Europe's population in just a few years. This type of disease is carried by bacteria, a bacteria called Yersinia pestis, which live on fleas, which are carried by rats, who were traveling on merchant ships coming from the east of Eastern Europe. And here you can see, based on the color, the map of the diffusion, with the green being the early areas that were affected, and then progressively until the dark brown, the latest areas to be infected by this disease. And the arrows show also the sense of this diffusion. So it took a few years, but since there were, people were defenseless, medicines were not very advanced, and the hygienic conditions of people were not really ideal, despite the fact that, of course, people were not traveling fast as they do today, this disease had really tragic consequences for Europe. So can we do something to stop it? Can we use network science to somehow at least contain that? That's what's been done, for instance, most recently in the case of the COVID pandemic, which is why I propose a kind of COVID pandemic simulation scenario as a project pitch last week. And I see that some of you have embraced that, so I'm curious to know what you find there. What are the main problems of epidemic spreading today? You can see, okay, now, of course, we have advanced medicine, of course, but at the same time, people are moving much faster because of the advances in the technology of transportation. Somebody gets Ebola in Africa, can travel to Europe, America, and Asia, and spread the disease before even displaying the first symptoms. And this is a very deadly disease. At the same time, technology has created new types of epidemics. Computer viruses and malware spread over the internet. And there are mobile phone viruses, which spread by Bluetooth or MMS. And there is, of course, also misinformation, which spreads through social media, which are now the privileged channels of communication and information between people. So not always progress is good. On the one hand, it helps us to contain epidemics, and probably we'll never have another Black Plague and Black Death, at least hopefully, because of that. But at the same time, it also facilitates the diffusion of epidemic because of the fact that people are moving much faster and they can carry then the disease much faster than before. And the way it happens is that of course, you need people of infectious diseases need, of course, for people to be close enough to each other to affect each other, to pass the disease on to another. And that's why ideally what we like to know, and it's a dynamic thing, is the network of contacts between people, physical contacts, so that which that people get close enough to each other to have a possibility of infecting them, for instance, like in the case of COVID. This is an example of a contact network. It's a very small one. This is a network of children in French school. The different colors indicate different classes, people of different ages. there is something here. In the contact network slide, what does the size of the node indicate? It's just the number of their contacts. I was about to say that. So these are people of different ages. As you see, first B, second B, fifth A, and so on is a bit older. As you can see, there are many contacts within them because, of course, people in the same class, children in the same class interact much more frequently with each other, but there are also contacts with the children of other classes because they have some common breaks in which they meet in common recreation areas to eat or to play in the park or other things. And the gray nodes indicate the teachers of the school, who also, of course, part of the epidemic dynamic because they interact, of course, closely with other students and with, I mean, in their class and in other classes, they usually have multiple classes to deal with. So and plus, you know, then of course, then you get it from children, and then you pass it on your own kids, family, and then the epidemic spreading continues. The way they kept track of this contact is very interesting. It's a project called Social Patterns, socialpatterns.org, I suppose. But if you look for social patterns in Google, you can easily find it. And actually, interestingly, I organized a conference independently of this where the first social pattern devices were deployed. So I was also wearing my own beacon, which is basically hanging on my neck like everybody else. This is a device that basically senses when people are close to you. So when you're interacting with somebody face to face, like for instance, a coffee break or just simply talking sufficiently close, then there is a signal exchange between these two devices. And that keeps track of how many pairs of people are interacting when, for how long. In the meantime, the technology is sophisticated. Now these things are much smaller and much cheaper, and they managed to scale this up a little bit. They deployed up to thousands of devices in specific contexts, including hospitals, major conferences, and so on. So there's a bunch of this data set. Of course, these are only proxies of what really happens. And for a real epidemic scenario in a big population, you will need to have, of course, the contact network for everybody, which is impossible, of course, to track down. So this, in fact, is one of the networks that I suggested you use for the project pitch about epidemic spreading, because, you know, it makes sense. It fits somehow the description. And but here I want to tell you something about basic epidemic models, the ones that everybody uses, although, of course, there are multiple variants of those. Classic epidemic models divide the population into compartments, which correspond to different stages of the disease. The most famous compartments are these three: susceptible, individuals who can, indicated with the letter S for susceptible, individuals who can contract the disease; infected, who are individuals who have contracted the disease and can transmit it to susceptible individuals; recovered, that those who recover from the disease and cannot be infected anymore. So we'll be playing mostly with this. So let me introduce you the first of these models. We introduced two, the most famous ones. And the second one has been used with a small modification to simulate a lot of epidemic scenarios in the context of the COVID-19 pandemic. So for the SIS model, susceptible, infected, susceptible model, there are only two compartments, susceptible and infected. So basically, when you can either get the disease, and once you get it, you become susceptible again. You can catch it again, which means this is a model which is good for diseases that you can catch multiple times because they don't give you long-lasting immunity. For instance, a common cold. You can catch a cold multiple times in the same season. And the dynamics works like this. A susceptible individual gets infected with a probability beta, which is called infection rate. And an infected individual recovers and becomes susceptible again with a probability mu, which is called recovery rate. So there are these two key parameters, beta and mu. And this is the way the situation is depicted here. You have the susceptible part of the population, the infected part of the population. Susceptible becomes infected with probability beta, and infected turns back to be susceptible with a probability mu. So if you simulate this on a network, which is what we are asking you to do, I mean, not SIS, the SIR model, but it's fairly similar. You take your network, which it could be either a random network that you build with a model or a real contact network like the one of these French school children. And you assume that initially there's a fraction of nodes which are infected, who are the first people who carry the disease, and you can either settle for a number or a fraction, like 1%. It's usually a good way to go. And you can also play with this number in your simulation, see what happens if the initial set of infected people is bigger than 1%, smaller than 1%, it's just a number, a single person, and see how much the result change because of that. And then you visit all the nodes in sequence. For each node I, if I is susceptible, you check the neighbors. For each infected neighbor, I becomes infected with probability beta, just like in the influence. I mean, similar to the influence cascade model, sorry, independent cascade model that I just introduced. In the case, actually, you loop over the neighbors of the active nodes. In this case, you can do the other way around. If I instead is infected, it becomes susceptible with probability mu. Again, you throw a number between 0 and 1, a random number, and then you check and compare it with this probability mu. If it's smaller than mu, then that node becomes susceptible again. Otherwise, it stays infected. The difference, now the SIR model, which is the other one, is a bit different because in this case, there is another compartment, and after you get the disease, you either heal or die. But either way, you will not be playing any role in the epidemic dynamics. You basically kind of remove from the system, which is also why R is used for removed, not only recovered. And this is a model that applies to diseases that confer long-lasting immunity, like the measles or the mumps, rubella, and in principle also COVID, except the COVID, given this big diffusion, its high infectiousness, mutates all the time, so it becomes a different one. And then even the immunity you got after when you were infected the first time is not going to protect you from getting it again a few months later. I got it twice myself. I know people who got it multiple times. So now we have three compartments, and the scheme is very similar. Again, you have probability beta and mu. The difference is that I recovers with probability mu, but then it is moved to this compartment R, which does not play any role in the epidemic dynamics because the only nodes which can change the state are S, the susceptible, and the infected. But the parameters are called the same way, and there are only two, like in the other case. There is just one extra compartment. This is the model I ask you to play with in the context of that project pitch on the COVID pandemic. And these are general features of all these models, how it works. You have an initial stage in which there are just a few people infected and things go slow and irregular. Then you usually have a ramp-up phase. It's like a wildfire in which, this thing spreads very fast and can quickly affect a large number of people. And then there is a stationary state in which the disease is either endemic, which means it ends up affecting a stable fraction of the population over time, or it is eradicated. In these two plots here, you can see the two possible evolution of the two dynamics we consider. This is SIS, and the bottom one is SIR. You see there are three compartments here indicated by the three lines. Here, there are only two lines. And this is a case in which, as you can see here, the fraction of infected eventually is stable at around 80%. And the fraction of susceptibles is around 20%. Because there are, of course, more fluctuations, but if you keep simulating this, then you will see that these plateaus are basically stable. And what that means is that basically that at any time after the transient, when the process starts, at any time, there's going to be around 80% of people who have the disease. And 20% of people who do not have it and can catch it again. And this is what happens actually in a real network in which there is just one initially infected individual, which is indicated by this orange dot. So it keeps spreading here. And the arrows indicate which stage, which time steps and which stage of the epidemic we're talking about. And you see these last two configurations are similar. And in fact, the variables, the main variables, the fraction of people in the two compartments is similar. But that does not mean that the nodes who are infected and the ones who are susceptible are the same, because at some point, if you are infected, you're gonna get healed, but then you can catch it again. So that's an example of dynamic equilibrium in which some measurements, in this case, the fraction of people who are in the two different compartments are fairly stable, but they do not comprise the same set of people. You can also see by comparing this diagram with this other diagram that some of the blue spots become orange and vice versa. But there is some sort of balance. For the SIR, instead, what you have is that at some point, of course, there will be no more susceptible people because people will get the disease and then will heal, that the number of recovered people keeps growing until it saturates, and that the number of infected peaks, the famous peak of the pandemic that you heard many times probably during COVID, waiting for the peak, and then, there is a descent until it goes to ideally reasonably small proportions, or even better, to zero. Eventually, in this dynamic, since as people get sick and recover, then eventually they're not going to be, of course, any more sick individuals. That's actually the main difference between the two models. Now let's focus a little bit more on how these dynamics play out on networks. We start with the hypothesis of homogeneous mixing, in which every individual is in contact with every other. This is pretty much the same as saying that you deal with a network in which everybody is connected to everybody else, which basically means that you deal with a monster clique. It's not a very realistic assumption. It's probably valid only for, it's generally valid only for very small groups in which indeed everybody eventually gets in touch with everybody else, but certainly not for the global population at large. So every individual is in contact with every other, and everyone is basically the same. There are no different structural roles because everybody is connected to everybody else. And that's not a valid assumption. I mean, I'm just saying that because people have worked a lot, especially at the beginning in the 60s and so on, when these epidemic models were introduced, with this kind of model in which everybody eventually gets in touch with everybody else. What's been clear in the last 15 to 20 years is that if you want to do the good job, you cannot neglect the fact that real contact networks are very different from this homogeneous mixing hypothesis, because it's not true that I get in touch with everybody in the world, right? I have my own contacts, and of course regular contacts, but I also have occasional contacts, meeting people that I never seen, I don't know, at the supermarket, in a pharmacy, or other opportunities, events, and other things. But it's certainly, of course, a very small number compared to all the people that I can get in touch with. So it is really critical to reconstruct the actual network of contacts. And so if you then try to model these two models, these two epidemics models on networks, what you usually do, you can, I mean, one thing that people do at the beginning is to assume that you have an homogeneous contact network with all nodes having degree approximately equal to k. So they're not in contact with everybody anymore, but they have approximately the same number of contacts. That would be the case, for instance, like an Hertzsprung/Gilbert model of random networks, in which eventually people are in touch with approximately the same number of individuals. Initially, of course, few people are infected, so you can assume that every infected individual is surrounded by susceptible individuals. So that the chance that two people who are infected are neighbors is small, even though if you think about it, given the way the epidemic propagates, then it would make still sense to consider that some of these people are neighbors in the contact network, because that's how then one of them got the disease. But let's assume instead that each of them is surrounded, only the neighbors are susceptible, and each infected individual can transmit the disease to about then average k people at each iteration, because that's the neighbors, the people that they get in touch with. So after one iteration, since you have a probability beta to infect each of your susceptible neighbors, and the number of susceptible neighbors is average k approximately, then you expect that after one iteration, each infected individual has infected beta times average k neighbors, contacts. Now, if there are I infected individuals, then after one iteration, you expect that the number of so-called secondary infections, to distinguish from the primary infections, which are the persons who get the disease first, is just this number times the number of infected people. Each of them, on average, infects beta times average k contacts, assuming that everybody is the same, approximately the same number of contacts, average k. On the other hand, after one iteration, each infected individual recovers with a probability mu, which means that at the end of the first iteration, you expect that a number mu times I of these infected individuals are recovered. And here the key consideration. The threshold condition for epidemic spreading is that the number of secondary infections should be larger than the number of people who recover. So basically that you spread the disease faster than you get out of it, then you recover from it. So if I compare these two numbers, the number of secondary infection and number of people who recover, infected people who recover, and this is the inequality that I'm interested in, I see that the threshold, this threshold condition can be read as this number here, beta divided by mu times average k, being larger than 1. This is the famous or infamous R naught that you may have heard about during COVID. And the number that people try as much as possible to keep low, because if this number is significantly larger than 1, then the epidemic is very infectious and very dangerous. It's called the basic reproduction number, R naught. It's just this ratio. If R0, R naught is smaller than 1, the initial outbreak dies out in a short time. There is no pandemic. Unfortunately, as it happened for COVID, R naught was initially between 2 and 3 for the very first strain, and then it went up to 8, 9, 10, and so on. Very, very contagious thing as the virus mutated. The epidemic instead, in this case, keeps spreading indefinitely. And of course, as long as there are people who can get infected. And that's why you eventually can infect a finite fraction of the population, which is, of course, a disaster, as it was in the case of COVID and of the Black Death in the Middle Age. Now, the problem is that this is all under the assumption that networks are homogeneous, in which all the nodes are approximately the same number of contacts, these contact networks, like in the case, for instance, of the random graph model of Erdős-Sarányi or Gilbert. I told you they are equivalent. But real contact networks are not homogeneous. There are people who are much more active, also because of the job that they do. I don't think about policemen, teachers, nurses, and other categories, people working grocery stores. People who are exposed, who can expose many more contacts than the average person. So in particular, these people are hubs, and of course, some of them are more hubs than others. And their presence of hubs changes drastically the scenario. On contact networks with hubs, there is effectively no epidemic threshold. Even a small infectiousness of the disease manages to affect a finite fraction of the population, even though this finite fraction of the population may end up being small. And the reason is that even if the infection rate is low, the process at some point eventually will reach a hub. Hubs are easy to reach through contacts. The neighbor, and so on increases the chance of bumping into a hub because they have many more links than the others. And once you affect the hub, of course, this person also has a lot of contacts, and some of these contacts will also get the disease. And by doing that, they will also affect other hubs and so on. So this is the reason. The presence of hubs makes epidemic spreading much more dangerous than it would be otherwise in a context of a homogeneous network. And unfortunately, we know that real contact networks are heterogeneous instead. So if networks of contacts as they are heterogeneous, how can you possibly contain the epidemic spreading? You can try to isolate, vaccinate individuals from many contacts. That would be obvious, right? If the hubs are the reason why these processes are spread so fast in real contact networks, the ideal thing is somehow to get rid of them, isolate them, or vaccinate them if you have a way for them not to contract the disease. But how do I know who the hubs on my contact networks are? As much information as we can have through the media and so on, we don't know. The authorities, departments, the Department of Epidemic Spreading labs, they don't know who I'm going to meet when I walk around today. So one thing that you can do, and we've seen it in the framework of the friendship paradox, is that we know that if we pick edges instead of picking or links instead of picking nodes, we have a higher probability of finding a hub. If I select, like in the case of the friendship paradox, we made this example. If I select a link, there is a higher chance that one of the two endpoints is a hub than if I just select 2 points at random, 2 nodes at random. And that's why somebody proposed something which looks like provocative, and this was restated also during the pandemic many years later, but the original suggestion of 2001, which is then picking people at random, so picking nodes at random, and then asking them who their friends are, the person that they are more regularly in contact with are. Because by doing that, what we're doing is basically we are following edges, we're following links from the nodes that we select to the neighbors that they declare. And by following that, there is a higher chance that their neighbors are hubs. That's the thing, the friendship paradox, right? That our neighbors, that our friends have more friends than we do. Of course, that's valid on average. And by doing that, in fact, we can easily see by doing simulations or any network that you can think of, which is sufficiently heterogeneous, that you would end up protecting the system better than if you just vaccinate a random fraction of nodes of people chosen at random. So vaccinate the friends of people that you choose at random, which is kind of funny, and hopefully one of the things you will remember from now on. A particular application of epidemic spreading models is in the context of gossip or rumor spreading. This is a model proposed by Daly and Kendall in the 60s in Nature paper, very short, very nice, which basically proposes a model which is basically an SIR model, but with its own rules, special rules, because of course the rules have to kind of match the type of process we're describing now, which is no longer the spreading of an epidemic of an infectious disease. So in this case, we have again 3 compartments: ignorant, spreaders, and stiflers. Ignorants are S, the susceptible that we had in epidemic spreading. Spreaders are I, and stiflers are R. Stiflers are people who know about the rumor, but they do not spread it because they don't think that there is an incentive. They think that there are enough people who know about it. And that's a basic idea of the model. People keep spreading the rumor until they feel that enough people know and they have no incentive to spread it further. And what happens is that when a spreader, I, approaches an ignorant S, the rumor is told and the ignorant becomes a spreader with a transmission probability. This is exactly the same thing that happens in SIR and SIS when an infected individual gets in touch with a susceptible individual. It's exactly the same thing. What is different is what happens when a spreader meets a stifler, when I meets R. In the SIR model, nothing happens because the recovered people do not play any role in the dynamics. Once they're healed, they cannot contract the disease because they have immunity, and they cannot pass it along to other people because they are healed. They don't have the disease anymore. Whereas in this case, when a spreader meets a stifler, the spreader becomes a stifler with a stop probability, which is the second parameter of this model. Instead of having a mu probability of recovering mu, we have a stop probability alpha. We're going to see it better in the next slide. When 2 spreaders meet, they both turn to stiflers with the same stop probability because they find out basically by meeting each other that they know about the rumor, so they don't have an incentive to spreading it further. So these are the 2 parameters, the transmission probability beta, just like in the case of the epidemic models, SIS and SIR that I showed you earlier. And then there is a stop probability alpha. And this is how the dynamic works. So the spreader manages to affect the ignorant with the probability beta, just like in the case of the epidemic models. And if that succeeds, then both of them are then spreaders. If a spreader meets a stifler, then it becomes a stifler with probability alpha. In this case, the effect goes from R to I, and you see both of them become R. And likewise, when 2 spreaders meet each other with a probability alpha, they both convert into stifler, which are the green dots here. And the dynamics works like this. You have a network, whatever you wish. You can make a model or make it with a model, or pick a data set that you like. That makes sense, a data set of contacts between people in communication, for instance. And for each I, you do a loop over all the nodes. For each I, if I is ignorant, so doesn't know anything about the gossip, you loop over the neighbors. For each spreader neighbor, I becomes a spreader with probability beta. Let me see. What is the logic behind 2 spreaders becoming stifler? It's the same idea as before. By meeting each other, they found out that they know about the gossip, and they have no incentive to, and they have the feeling that enough people know about the gossip, so they have no incentive to spread it any further. So they stop spreading it. They say enough people know, so it's the same criterion for the 2 processes. When a spreader met a stifler and when the spreader met a spreader, meets a spreader. So you loop over all the nodes. You can do it again synchronously or asynchronously in random order. Okay, thanks. Okay, sorry. If I is a spreader, if I is an ignorant, you check over the neighbor. Sorry, I already said that. And if I is a spreader, loop over its neighbors. For each stifler neighbor, I becomes a stifler with probability alpha. for each spreader neighbor, I and the neighbor both become stiflers with probability alpha. So you do that, and that's how the dynamics proceeds. Now, what's the important difference with the SIR from the SIR model that I emphasized already is that the transition from infected to recover, in this case from spreaders to stifler, does not occur spontaneously. They have to meet. So in epidemic spreading, instead, you lose the diseases by curing the disease. You recover from the disease by yourself. You don't need to interact with anybody to lose the disease, to get out of the infectious state. Whereas in this case, you need to meet a stifler to lose the incentive of spreading the rumor further. In this case, turning into a stifler. Like in the SIR model, starting from a few spreaders, eventually all individuals will be either ignorant or stiflers, because in this final state, of course, the dynamics cannot produce any change. If you have no spreaders, nothing can happen, because ignorant and stiflers do not interact with each other. And then there is no threshold effect, and that's another difference from the case of both the SIR model and the SIS model. The rumor can reach a large number of people, even if the transmission probability is low, both on homogeneous and heterogeneous networks, because of the hubs again. Okay, that was a curiosity of how we can use a framework which is similar to the one of epidemic spreading to model something different, like in this case, the spreading of a rumor. And then we tackle now the final class of models and dynamics that you can that I wanted to let you know about. Of course, there are so many more processes that you can run on a network based on whatever problem you have in mind, that it would have taken much longer somehow to go over all of them. So I decided to cover information diffusion, epidemic spreading, and opinion dynamics. Needless to say, opinion dynamics is very important. It determines how opinions form and diffuse in society, and now they spread on social networks, networks of Facebook friends, networks of Twitter followers, following networks, and Instagram, and of course your TikTok and all the things that you're probably more familiar with than I am. The model is actually similar to models of inference spreading. We'll see what the differences are. In some cases, in actually one case that I'm going to emphasize shortly, they are exactly the same. And usually an opinion is represented by a number or a set of numbers, like a vector, but we'll be sticking to a single number. Is there an R0 for rumor spreading model like the SIR model? That's a good question. Not exactly, because I mean, you can of course always compare the secondary infections with the number of people, the spreaders who recover, but you cannot simply do the construction that leads to the formulation of that simple equations that you've seen. So basically, the answer is that in principle, yes, of course, you can define the conditions that that lead to either the suppression of the diffusion of the gossip right away, or to a major spreading across the population. But it's not as simple as in the case of epidemic spreading models on homogeneous networks. But thanks for the question. Yes, thank you. Yeah, sure. In fact, that could have been something interesting. Why don't you derive a formulation like that? I already showed you how to do it for epidemic spreading. See how far you can go within this is a separate thing. I'm sure that you already decided which project you're going to join. But also for the future, for your own curiosity, it wouldn't be difficult to to play a little bit and see what I told you, that it's not going to be so easy to formulate this in a closed fashion, with the defining basically an indicator, a variable like the R0. But in principle, it's possible. You can define the condition because the process is the same. You just have to make sure that the thing spreads faster than it stops spreading. That's the condition that keeps the thing running. Otherwise, eventually it dies out very quickly. So we'll be assuming that the opinion is just a number, and we have two classes of models, whether the opinion is integer or if it's a real value. The first case, we talked about discrete opinion dynamic models. In the second case, we talk about continuous opinion dynamics models, and these are the ones we're going to cover, the main ones. Now, for discrete opinions, we can think about the scenarios in which people have a limited number of options, and actually we just limit them to 2 options, although of course in principle you can have more than 2, like right, left, the Republican, Democrat, abortion or pro-life, pro-abortion or pro-life, buy, sell. And we indicate in this case is two options with the numbers 0 and 1. But you can choose any two numbers. Some people choose -1 and 1 to emphasize the contraposition. But in this case, we're going to use 0 and 1. A model is characterized, of course, by the set of rules that determine how the opinion of a node changes due to the opinions of its neighbors, just like in the cases of the dynamics we introduced so far in other contexts. So initially, again, you have, actually, no, there's a difference with the other models. Initially, everybody has opinions. You don't need to get opinions if you don't. I mean, of course, some people may be undecided, maybe kind of fluctuate, swing between opinions. And actually, especially for elections, this is very important because people instead who have strong opinions, they're hard to change. So the ones that you can try to convince are the so-called independent, that sometimes whose opinions swing, the so-called swing voters. But in this case, the initial configuration, everybody has an opinion of some sort. So in this case, some people will have opinion 0, some other people will have opinion 1. And a very traditional way to start the simulation is just by assigning opinions set randomly to all the nodes. So basically, you can expect to have about half of the people having opinion 0 and half of the people having opinion 1. So this would be an initial configuration in which there is disagreement because there are basically two parties. So basically, polarization of the population. And then you update the opinion over and over opinion rule, whatever, which is the ones of the model that you choose. There are many, many models that you can select for this. I'm going to introduce 2 of them, but there are many more than 2, including many variants of these 2. And as you repeat applying these rules and so on, then you see that the opinions can change, and then there are final states which can, in which the disagreement may disappear and you have consensus, everybody reaches agreement to one opinion, either 0 or 1, or you can still have disagreement. And in this case, I mean, we can check how many people of the 2 opposite opinions you have at the end, if you have a final state. I'm going to say this shortly. So an iteration consists, again, in running a loop over all the nodes, and you can do this asynchronously in random order. This is the way I've always been doing it, but you can also do it synchronously. And there are 2 possible outcomes. The system reaches a steady state where no node changes its opinion anymore. That's a steady state. So everybody sticks to an opinion and doesn't change it anymore. This state can be consensus, with all nodes having the same opinion, or polarization, when some nodes have an opinion and the rest have the other opinion. If you think of inference opinion, this is stage as a states of nodes. In that case, all 3 scenarios always have an initial state. If we think of inference opinion, disease stage as states of nodes, in that case, all 3 scenarios always have an initial state. Oh yeah, you can say, yeah, that the initial state is that, active, inactive. Yeah, in this respect, yes, indeed. So in principle, yeah, we can make this analogy. So technically, you're right. Sorry. Consensus is then a potential outcome of the dynamics in which everybody has the same opinion. Otherwise, you have polarization in which some nodes have opinion 0 and the others have opinion 1. But it's also possible the system does not reach a stationary state because there are nodes changing opinion all the time. Still, even in those cases, sometimes, not always, you may have what is called a dynamic equilibrium, like the ones that we've seen for the SIS model, in which there was a fraction of nodes which was always infected, but it's not the same, but would not correspond to the same individuals all the time, because they get in and out of the state. They get susceptible and then infected again and so on. And the same thing here. They will swing between the 2 opinion states, opinion variables, opinion values, but in a way that basically keeps the relative proportions of these 2 opinions in the population approximately stable. What do you measure in a system like this? One thing that you can measure is the average opinion, which is literally the arithmetic average of the opinions across the nodes. So if you start from a random distribution of 2 opinions and the opinions are 0 and 1, like in our case, the average is around 0.5, because half of the people will have opinion 0 and the other half will have opinion 1. So the average opinion usually changes during the dynamics, and one can keep track of its value after each iteration. So you can do a nice plot like we see in the case of the epidemic dynamic, in which at each time step, which would be an iteration, a sweep over all the nodes. After you do that, you check the average opinion and you keep track of this as time changes with the number of iterations and see if this number eventually converges to a value or if it keeps swinging wildly. That really depends on the rules of your opinion dynamic. If the system reaches a stationary state, the average converges to a precise value, so you reach a plateau. If the stationary state is consensus, then eventually the average opinion will be either 0 or 1, because all the opinions will be equal to 0 or equal to 1. Now, let me introduce something a little bit more intricate, which is the exit probability. This is a key concept that's been studied for years for a lot of these dynamic models, even those which are technically not opinion dynamic models. And I give you an example here. The exit probability is defined as the probability that the network reaches consensus to opinion 1 as a function of the fractional nodes with opinion 1 in the initial configuration. It gives us an idea of how easy it is for the model, for the system to reach consensus around opinion 1, one of the two opinions. We select 1 for, convenience, but could be 0 as well. Let's stick to 1 in this case. Let me give an example. Suppose that we run the model dynamics 100 times, starting from 100 different random configurations. In each initial configuration, we assign opinion 1 to every node with probability 0.4. So initially, approximately 40% of the nodes will have opinion 1, and the other 60% will have opinion 0. It's approximate because it's a stochastic process. If all runs lead to consensus, and 30 of them to consensus to opinion 1, then the value of the exit probability for this initial probability 0.4 of having opinion 1 in the initial state is 30 divided by 100 equals 0.3. So you just check how many times your simulation converges to everybody having opinion 1. And you connect that, you make a plot. So the exit probability is a diagram. It's not a value. It's a function. It's a function of the fraction of nodes initially in opinion state 1. It's going to be a bit more clear when I show you some example. So let me give you then, let me introduce then the two main models that I'm going to talk about here, about discrete opinion dynamics. One is the majority rule model, in which each node takes the opinion of the majority of its neighbors. So in this way, somehow it looks like the threshold model that we've seen before. And in fact, there is a strong relation that's indicated by this line here. So but let me get to there a bit more slowly than that. If the number of neighbors is even, so if you have, say 6 neighbors, 3 of them have opinion 0, 3 of them have opinion 1, then you pick one of them at random. So you break the tie randomly. Or like I say here, flip a coin, which is the same thing. In fact, this is exactly equivalent to the fractional threshold model of information diffusion with threshold 1/2, because in the fractional threshold model of information diffusion, you need to have 1/2 or more of the neighbors in the active state to switch to the active state. And of course, instead, if you have less than that, you do not switch, so you remain inactive. So this is an example here in this diagram A. This is the focal node, which I made a bit larger here. It has 5 neighbors. 3 of them are in the red state, say opinion 1, and 2 of them are in the blue state, say opinion 0, then the node remains in the same, with opinion 1. So what are the stable states of this opinion dynamics? A stable state is consensus, but it's not the only one. Consensus, of course, because the moment everybody has the same opinion, then nothing can change anymore. So the system is stable, and no, there cannot be any more opinion changes. But there are also states, interesting states with opinion coexistence. They are stable because each node has the majority opinion of its neighbors. It can happen, especially on lattices. But it happens, in fact, also in pretty much most of the graphs you can think about. And in fact, in most of these graphs, and certainly the ones that we introduced in this course, the majority model never reaches consensus. There have always been some nodes with opinion 0, some nodes with opinion 1. But that would be a stationary state, because each node has no incentive to change its opinion because it will be surrounded by mostly nodes with the same opinion. Oh, we see you, not your presentation. Okay, I see the presentation as well. Okay, anybody besides Annika who does not see? I see the presentation. So apparently there is something, I don't know, Annika, you can perhaps try to get in and out of Zoom. So
No, I
does
don't
anybody
think
else? Yes?
I can see the presentation.
Yeah, thank you. I mean, does anybody else not see? I'm good here. It seems to be more like a problem on Annika's side. So I would suggest maybe to get out of Zoom and back in again quickly, and hopefully things will be solved by then. Sorry about that, but it seems to be good for. Sorry, thank you. I see the presentation. Check your Zoom. Swipe right on the screen. Yeah, sorry about that. Hopefully, let me know if you can fix this. Luckily, I mean, the slides are available. You can get them from our Dropbox folder and you can follow them. I mean, it's not ideal, of course, but I would first solve the Zoom problem by just trying to get in and out of the system. So like I said, basically in all the models of networks that we've seen so far, this model, this majority model, will not reach consensus. It will get locked in configurations in which some nodes will have opinion zeros and some nodes will have opinion one, because each of them would be surrounded by a majority of nodes in the same opinion state. Link to the slide. Thank you, Satyaki. That will help. So on the other hand, if you consider one and two-dimensional grids like lattices, one would be just a line with the nodes, having two neighbors each on both sides, and the square lattice already given examples of this. In those examples, for instance, one-dimensional strings, the system always gets to consensus. In two-dimensional grids, actually gets to consensus with two-third probability. And with the one-third probability around, it's not exactly two-thirds, it's been determined empirically. And with the probability one-third of the runs that you make will get locked into a configuration where you have straight interfaces, where you can have, I don't know, half of the lattice is blue and half is red, not necessarily, and actually, or even just a stripe is blue and a stripe is red, but you can also have multiple stripes, because along each stripe, the so-called interface, each node is surrounded by three neighbors of the same color. So that's actually exactly this interface thing is what basically locks the system into this stable but not consensus configuration. The exit probability for the runs leading to consensus, because you cannot define the exit probability unless you get to a consensus state, to either 0 or 1, is a step function. This is actually the most common profile of the exit probability that you can get by running opinion dynamics with discrete opinions. And what that means is that if you have less than 50% of nodes initially with opinion 1, you will never get consensus to opinion 1. So there is some sort of majority rule. If you are in the majority at the beginning, you will be dominating the other opinion at the end, all the time. So like in this case, if you have more than 50%, so if you're past this 1/2 threshold here, more than 50% of opinions of people, nodes, with opinion 1, then everybody will have opinion 1 at the end, systematically, with no exceptions. This is pretty interesting, and it's what happens in most things. So there is some sort of kind of, basically the majority rule, in which if you are in the majority initially, basically you will impose your opinion to the rest of the system. But that's not what happens all the time. And that's not what happens for the voter model, which is my next customer here. Let me see. Exit probability depends on the network structure, right? Is step profile for lattice? Yes. No, actually, I mean, with few exceptions, unless you go to the one-dimensional case, which is not even, I mean, kind of a very strange network, very simple, right? Like a string with nodes which have two neighbors each. Unless you go there, where you can get some strange profiles, usually you get either the step function that you've seen, or the diagonal that you're going to introduce in the next slide. So it doesn't really depend on the network. Is this model realistic? Most opinions I can think are not very consensual among people. Which one? The voter model? The voter model I haven't introduced yet. Not very consensual among people. Yeah, of course. I mean, it's not. Of course not. These are not realistic models, but they've been used as key ingredients to for models which are more realistic. I'm going to introduce some things. I'm going to give you ideas on how you can make these things a little bit more believable. These are mostly mathematical construction people have been playing with, just to derive some nice laws and critical exponents, that kind of stuff that statistical physics like. But to turn them into realistic models, you will need to work some more to relax some of the assumption. So that's a good point. Definitely they're not realistic. And this one is also not realistic. The voter model, which has been around for a very long time, in which basically each node takes the opinion of a randomly chosen neighbor. The good thing of the voter model is that by applying this dynamic, eventually everybody will have the same opinion. You just have to wait long enough because the convergence process is slow. On any network that we see, any network you can think of, it's the only stable state of the model. So let me just summarize it here. This is the same situation we've seen before, in which there is this big red node, which has 3 red neighbors and 2 blue neighbors. The difference is that in this case, this red node, which cannot change its opinion state according to the majority rule model, because the majority of its neighbors is already in its opinion state, so it's in a stable configuration. In the case of the bottom model, instead, it can change the state as long as there are blue neighbors around, because there is always a possibility to pick randomly one of these blue nodes. This is exactly what happens here. Of course, if you don't have many blue nodes among your neighbors, then the chance of turning blue is low, but low doesn't mean 0. And that's the reason why consensus is the only stable state of this model, which has been studied for many years, which is analytically solvable exactly in all dimensions, in lattices of all dimensions. Are the edges weighted? No. But of course, you can easily extend this to the case of weighted edges. In this case, you can say I pick a node proportionally to the weight of the link connecting me to that node. Now, yeah, I'm talking about unweighted networks. In fact, most of this work is about lattices, but some of the conclusions are the same. And some are different, actually, especially if you move from lattices to heterogeneous network like Barabasi-Albert networks and so on. But I'm not going to talk about this here. Again, this is part of the more in-depth stuff that, if you want to get more information about this, I'm happy to provide offline, but they're not part of this introductory course. So now here we just select the event random, assuming that all the weights are the same. How do you just there is another. Oh, so the voter model is like independent cascade pairwise interaction. In a sense, yes. The difference is that the probability of switching is exactly 1, right? Because once you pick a neighbor, you always get the opinion of that neighbor. Yeah, I mean, there's not so much you can do at a very basic level about this model. Some of these models resemble each other, and I showed you already a majority rule model is basically equivalent to the fractional threshold model with threshold 1/2. But this is instead more about, again, pairwise interaction. So in a sense, yes, more similar to independence cascade model, only there are no probabilities of convincing the pair because you systematically adopt the opinion of the chosen neighbor. The exit probability in this case for all instances of the voter model on any network you can think of, including weighted ones, is a diagonal. So it's not a stepwise function like before, step-like function, which means basically even if you start with an initial fraction of opinion 1, which is less than 50%, you have a probability of obtaining consensus to opinion 1. So even a minority of opinions can turn everybody else into that opinion. Of course, the smaller that opinion, the lower the chance that this is going to happen. But it is possible. So this is a very peculiar feature of the motor model and basically no other model, because most of the other models have this stepwise, step-like function that you've seen before for the exit probability. So if you are in the majority at the beginning, you will basically dominate at the end. Whereas here, if you are in the majority at the beginning, you can still lose the race to the other opinion. So specifically, I give an example here. If you have 30% of the nodes, so approximately here, in the initial of opinion 1, in the initial configuration, then in about 30% of the runs, if you then have a bunch of runs, initially with 30% of nodes in opinion 1 and 70% opinion 0, you will see that about 30% of the runs will converge to consensus to opinion 1, and the other 70% to consensus to opinion 0. So like someone mentioned, these are not very realistic models, so people have proposed a bunch of variants of those to make it a little bit more realistic. For instance, there may be people who cannot change their mind. These are called zealots. Nodes who never change their opinion, but on the other hand, they can change the opinions of their neighbors. So if you have zealots and all of them have the same opinion, they will favor consensus around that opinion. In fact, if you are on the square lattice, a single zealot managed to switch everybody to consensus to that opinion in the long run. It's a very slow process, but eventually we converge to that. If you are in 3 or more dimensions, instead, you're going to get coexistence of opinions. But around that zealot, you're going to have some sort of polarization in which you have mostly nodes with the same opinion as the zealot. You can also consider more the 2 opinion states, 3, 4, 5, 10, and more. And you can change a little bit the update rule based on that. For instance, in what is called the constrained voter model, which is in the meantime kind of 20 years old, Mobilia et al., you have 3 opinions, but only neighboring opinions can interact. So 1 can interact with 2, 2 can interact with 3, which means if I'm 1 and I pick a random neighbor and the random neighbor has opinion 3, then I'm not going to take opinion 3. Whereas if I pick a random neighbor and the opinion neighbor is, and the neighbor's opinion is 2, then my opinion becomes 2. And the same thing for 2 and 3. This is interesting because it leads to more elaborate and more complex scenarios at the end. Consensus is actually still possible. It's still definitely a stable state because once everybody's on the same, has the same opinion value, then nothing can change anymore, according to the dynamics. But much more common in this case for the constrained voter model is to get states in which the 2 extreme positions coexist. So you have a bunch of nodes with opinion 1, a bunch of nodes with opinion 3, because the opinions 1 and 3 cannot change each other. So you see, with a small modification, you can get more elaborate scenarios. And the other thing, which is something that people have imported in many different models, not only on this one, is the possibility for nodes to change their opinion spontaneously. So introduce some probability on top of the voter dynamics, and at the end of one iteration, you can do another iteration over all the nodes, and you change the opinion of each node with the probability P. In this case, as you can imagine, there's never going to be consensus because you keep changing the opinion all the time. So there's going to be always a fraction of, even if there is a majority of one opinion, there's going to be always a fraction of people of the other opinion. And this actually is a dynamic thing because then you can change your opinion in principle at each iteration. Okay, that's as much as I wanted to tell you about discrete opinion dynamics models. Let me actually check what time it is. Lack of time. Thanks for the questions, by the way. Okay. There is something else here. Oh, okay. In dynamic models, can we also change the links? Considering a node which has recently changed does not have straight connection. I think there's no matter. Very nice. Yes, and I don't know if you read probably didn't read the slides already, but I'm gonna mention something like that, a model of coevolution of states and structure. The model of Holman-Newman 2005 is almost 20 years old at the end of this. It's gonna be my last topic for today. So thanks for the question. It's very insightful. And in fact, I'm gonna give a big rationale why this would be a more realistic framework than these models that have been introduced so far. Okay, so let's move now to continuous opinions, to continuous opinions. In this case, of course, we have a spectrum of values. You have 2 extremes and everything in between the extremes. For instance, -1 and 1 could be the extremes, and then you have all the possible values between -1 and 1. That would indicate a situation in which you have some like continuous adjustment of your position, which would be, for instance, the case in the parliament, or Congress. In this case, you have the extreme right, the extreme left, and a bunch of positions in the middle that vary smoothly between each other. And in this case, again, you can choose to assign opinions randomly, taking from this range. But you have to introduce a stopping criterion, because now that you have real values, these numbers will always change a little bit, because real numbers, of course, are infinite figures, infinite digits, and of course, your computer will never, of course, reach the precise definition of these numbers. Cannot really store infinite digits. So you have to introduce a stopping criterion. The stopping criterion is that I stop when, between two consecutive iterations, the largest variation of any opinion is smaller than a predefinite threshold. So usually introduce something, I don't know, usually do 10 to the minus 4. I said if each opinion is changed by less of 10 to the minus 4, so it's a relative change, then it means that the two iterations are the same configuration. And you say, in this case, that the system has reached a stationary state. The possible stationary states that you can get with this, I like actually continuous dynamics models, opinion dynamics models. I worked with them at the very beginning of my career. I had a lot of fun, produced a bunch of papers, and because it's more, they can surprise you. They can lead to different scenarios, much more complex than when you have just a handful of opinions, like for discrete opinion dynamic models. Precisely, you can have, at possible stationary states, you can have consensus. Everybody gets the same opinion values. You can have polarization. Then there are two opinion values. Or you can have fragmentation. You can have multiple peaks of opinions. The only model of this class I'm going to introduce is probably the most famous one that I call the bounded confidence model. Some people call it the diffusion et al. Model from the name of their inventors. It was introduced in the year 2000, so it has, at the meantime, a quarter of a century. But I've been playing with it since the early 2000s. So I also had conjecture about this model, which has been then proved analytically by some mathematicians a few years later. And I'm going to mention this to you soon. In fact, could have been one of the project pitches, but in the end, I decided not to give it to you, to give something a bit more elaborate than that. So what is the principle of bounded confidence? Is that, again, this is a realistic ingredient. I mean, people can, of course, talk and convince each other of their positions, but only if their positions are not too far away from each other. Because it's kind of difficult. The two extremists on opposite sides of the spectrum can convince the other, one of them can convince the other of their own position. It never happens. So basically, the principle is that as long as the opinions are sufficiently close, then they can affect each other. What sufficiently close means, it means that their difference is smaller than a value, which is called confidence bound. If the difference of the two opinions, which are two numbers, is smaller than this in absolute value, smaller than this epsilon, confidence bound, then they can interact. Otherwise, they will stay, the two actors, the two individuals will stay in their own opinion. They will not change each other's opinion. And the other parameter is the convergence parameter mu, of this bounded confidence model, which basically tells you how much, when the two opinions change, how much they change, how much they move towards each other. So let me show you that with these very simple formulas. It should be clearer than in words. And this is how it works. You have a network, any kind. At iteration t, each node I is opinion OIT, which is a real number, say between 0 and 1. An iteration consists of a sweep over all the nodes synchronously or asynchronously in random order. This is what you do all the time for this type of models, including for epidemic spreading, information diffusion. At the next iteration t+1, for each node I, we pick one neighbor j at random. If the difference between the opinions of I and j at that moment is smaller in absolute value, is smaller than the confidence bound epsilon, then the opinions of I and j are changed as follows. So this is where the parameter mu, convergence parameter, plays a role. So it tells you by how much I moves towards the opinions of I moves towards the opinions of j and vice versa. So basically, after the interaction, the opinions of I and j are a little bit closer to each other than they were before the interaction. So these are, again, the same formula, nothing changed. If mu is equal to 1/2, if you put 1/2 here, you can easily see that both opinions converge to their average. Because here you get OI t plus OJT divided by 2, and here you get the same thing. And in fact, that's what people usually do. They usually set mu equal to 1/2 in order to actually accelerate the convergence. In this case, every time to people whose opinions are compatible meaning that their difference is smaller than the confidence bound, every time this happens, then they converge to the middle, their mean. But in principle, we can choose values which are smaller than 1/2. If mu is equal to 0, of course, nothing happens. If mu is equal to 0, OI at t plus 1 takes the value of I at times t. So everybody stays in their own opinion. So 0, of course, is not an option. It should be bigger than 0. It should not be bigger than 1/2, because if it's bigger than 1/2, then basically what happens is that you overshoot. I mean, you actually you move closer to OJ than OJ itself, in a sense, at the beginning. So that's not realistic. And in fact, if mu is equal to 1, they just exchange their opinions, which is not very realistic. So usually mu has to vary between 0 and 1/2. And people choose 1/2. Also because the final states of this model do not really depend on the choice of the parameter mu in this range. The parameter mu basically only affects the time to get to convergence. And since people want to get results fast, usually people choose 1/2 for mu, and they only play with the parameter epsilon, which is the only real parameter that determines the behavior and the type of stationary states that you get at the end. Another nice thing that you see here is that if I sum these two equations side by side and I divide by 2, here I get the average of the opinions of I and j at times t plus 1. And these two terms here are equal and opposite, as you can see. When I sum these two sides then and I divide by 2, I also get OI t plus OJ t divided by 2. So basically the average opinion of I and j is the same before and after the interaction, even if the opinions change. So these opinions, this dynamic preserves the average of the opinions. So if the initial opinions are taken at random from the range 0, 1, initially you have approximately average opinion 1/2. According to this result that I just told you, the average opinion of the system, even if the opinions change all the time, is going to be 1/2 every step of the way, from the beginning till the convergence to a stationary state. Specifically, if the stationary state is consensus, then the only possible value of opinion, which is going to be the same for everybody, must be 1/2, because otherwise the average is not going to be 1/2. This is something that you can easily verify. This is an extremely simple model to simulate and implement. There may even be already some code somewhere available for this, but it's very simple to do it, based also what you know now about networks and dynamics. So let me give you some more information about this model. We start from a random initial opinion configuration, again, from 0 to 1. Like, for instance, in this case, you see the opinions are distributed between 0 and 1 uniformly. This is time. And then you see as time evolves, then you form these two parties. For epsilon equal to 0.25, you have two opinions. But, I mean, this is the case in which everybody interacts with everybody else. So basically, in which you have a giant clique. The values of the confidence bounds, which leads to the formation of consensus or polarization, like in this case, 3 parties, 4 parties, and so on, 3 position, 4 position, and so on, depends on the network structure. And a lot has been done on lattices, heterogeneous networks, random graphs, like Erdős-Rényi/Gilbert, and so on, and you can see it for yourself what changes when you change epsilon in those cases. Like I said, the convergence parameter only affects the number of iterations needed to reach convergence, which is why you can just set the value to that, usually 1/2, and then forget about it entirely. Whereas the number of clusters at the end of the process depends on the confidence bound epsilon, and of course on the structure of the network. The lower the confidence bound, the larger the number of final opinions clusters. And this is my conjecture here. If epsilon is bigger than 1/2, the system always reaches consensus on any network with the opinions centered around 1/2. This is my conjecture, which has been then proven many years ago, more than 20 years ago, which was proven then eventually by mathematicians a few years later. So if your epsilon is bigger than 1/2, eventually the only possible state at the end is consensus on any network, whether it's a line or a square lattice or a Erdős-Rényi random graph or a Barabasi-Albert network, anything. You can, if you want, you can check it for yourself. So again, these are very simple models. There is this nice ingredient about the bounded confidence, the fact that opinions has to be close enough to each other in order to affect each other. And other, of course, things that you can introduce to make it more realistic. For instance, you can use individual values of the confidence bound because not everybody can be convinced as easily as everybody else. You can say, to convince me, somebody has to have an opinion which is sufficiently close to mine to pull me in that direction. And actually, you can also do something that was done already in the original version of the model as a potential variant in the original paper by Defan et al. That introduced the model. You can make this confidence bound depend on the individual's opinion. So if you are close to the extremes of the range and your range is, say, from 0 to 1, and your opinion is close to 0, close to 1, you can have a very low epsilon, indicating that if you are an extremist, it's very unlikely that you can be convinced by people who are not as extremist as you are, or close enough to that. But this is one of the many variants that you can introduce, and the other one is the one that I already mentioned in the context of the voter model, in which you have a probability of changing your opinion spontaneously. So at each iteration, you can loop over all the nodes after you updated them with the bounded confidence rule, and with the probability that you choose, you can change the value of the opinions of each node. But these are only some of the things that you can do. People, of course, over the years have proposed things which are more elaborate. They played with many different things. It's very difficult today to come up with something really original about these models, as it usually happens when stuff has been around for a long time. But this is fun, to play with that and to learn them. Perhaps it can inspire you to propose something different. And this is the last topic, which was actually mentioned in a remark before, about the co-evolution of networks and dynamics. So let me then make first a general consideration. And this page somehow is a very, very short summary of what is actually a very active topic within social network analysis and computational social science. The origin of network assortativity or homophily in networks. Why are we similar to each other? How do we get similar to each other? In social networks, there are two mechanisms that determine the observed assortativity. We usually tend to go around with people who are like us. Nodes are similar to their neighbors. So there are two possible things that lead to this result that you observe, in real networks. One is selection. Basically, I choose to become friend or to associate myself with people like me. And the other thing is social influence. I mean, I get influenced by people who are in touch with me. And that is the $1 million question in, among others, to some extent, in some parts of sociology, like I said, social network analysis, which is this. We observe that nodes are similar to their neighbors, but are we similar because we are connected, or are we connected because we are similar? If we are similar because we are connected, we are saying that we influence each other through our interaction. If we are connected because we are similar, it means that we are choosing each other. And there are some nice results also showing that in a big debate between the Christakis-Fowler franchise on one hand and some hardcore statisticians on the other hand, and the latter have claimed that there are no observational studies if you have some data sets, unless you make a control experiment. But if you cannot make a control experiment, so all you have is data, you cannot rule out one mechanism in favor of the other. You cannot tell whether the assortativity comes from selection or social influence, because there are a bunch of factors which are confounded, and selection may be hidden even if you do not see it. But anyway, this is a separate thing. And again, I'm happy to provide more details, but this is kind of more technical stuff. So be aware that if you read this, even myself, when I read that paper about statistics, that the argument why you cannot really discriminate between these two effects in observational studies, it's highly non-trivial. Every year I learn a little bit more about this. Okay, that said, that opens somehow the way to my last argument, my last topic, which is this. The limits of the models that you've seen so far, specifically opinion dynamics model, is the fact that the network is fixed. Once you have it there, You cannot have selection. You cannot choose to be together with people like yourself. In this case, people who have your opinion. So nodes with very similar opinions do not have the option to become neighbors unless they already are. Likewise, neighbors with very dissimilar opinions cannot become disconnected because you cannot move the links, right? Your network is stable. That's why many years ago, starting in 2005, in a beautiful paper by Peter Holm and Mark Newman, the first coevolution model has been proposed, in which both the opinion and the structure of the network change, and they change in a symbiotic way. Opinion changes may induce modifications in network structure, which could in turn affect your opinions and so on. So kind of a feedback loop. So we consider opinions as discrete in this model. Basically, I'm just going to tell you the gist of the Holm and Newman model that you can see represented here, the two possible things. Again, you do each iteration is a sweep over the nodes, synchronously or in random order. You've seen this for the other dynamics as well. Nothing has changed. For each node I, you select a random neighbor J, like in this case, blue, you select a random neighbor J with different opinions from J. So this is blue, I choose another color than blue. I have green neighbors, I have red neighbors. Let's suppose that I pick these green neighbors, red neighbors. With the probability P, the link between I and J is rewired from I to a non-neighbor, so somebody, of course, is not already a neighbor of I, who has the same opinion. So in this case, with probability P, blue is attached to another blue node, which was not a neighbor before. This is selection. I choose to become friends of somebody like me. Whereas with probability 1 minus P, that would be the second thing that happens, in alternative to the first, I takes the opinion of J. That's influence. So we are connected and we change our state because of our interaction. That's social influence. So selection and influence play together and in this model, which is a beautiful model. It's nice, and I like to play with that. And I propose my own coevolution model. I propose actually a coevolution version of the bounded confidence model of continuous opinions that I just introduced. People about how homophilia, okay, yeah, right. Yes, Charisse and Thomas. Yeah, that's, I don't know if it's a good thing or not, because this is really painful to read. But thanks a lot. Yeah, that's the paper that I had in mind. So, so this is actually an example of an evolution of this model. At the beginning, in this case, suppose that you have only two opinion states. And you see that at the end, you get a situation in which you have basically two connected components. The network is disconnected, and there are links only between nodes with the same color, because this is the only stationary state, the only stable state of this dynamic. Because every time there are nodes, connected nodes, neighboring nodes with different opinions, then the dynamics keeps going. So that's what you get at the end. If you have a bunch of opinions, that at the end, the system will organize into connected components, with each component having only nodes with one opinion state, like in this case. Once you get to that, of course, nothing can change anymore, because all the pairs of connected nodes have the same opinion, and therefore the dynamic cannot change anything anymore. Now, the very last thing is just basically at a high level how this network, how this system works, how this dynamic proceeds. If P is close to 0, so the selection probability is close to 0, then the dynamics is dominated by influence, by the influence mechanism, and the network structure barely changes, because if you cannot rewire your links, basically the network remains the same. So what happens in this case, the system basically homogenizes the opinions within the connected components of the initial network. If the network was originally divided into pieces, connected components, the opinions will become all the same within each component. And of course, they don't need to be the same across components. You can have, like in the previous case, a blue component and a red component, or you can have two blue components and one red component. It depends on. And if you have more than two opinions, you can have a bunch of scenarios. But within each component, you have the same opinion at the end, because this would be the stable state. On the other hand, if you have only selection almost, basically if P is close to 1, selection dominates then, and opinions hardly influence each other. So opinions are kind of static, and the only thing you do is just change the structure of the network. So basically what you do, people with similar opinion, with the same opinion, will search for each other and associate. So basically what you have at the end, you will form components around the groups of nodes which had the same opinion initially. Now, what happens when the number of opinions is large, more than 2, like in the case that we simulated in the picture seen before? If you start from a random network, let's say Erdős-Rényi/Gilbert with average degree larger than 1, this network has a giant component. This is one of the key results of the Erdős-Rényi franchise of the 50s already. For P near 0, in the long run, there will be a giant component holding the majority opinion and many small communities with different opinions. When P is near 1, there is only selection. The link dynamics will break the network into small components, which components basically is a subset of nodes with the same opinion initially. Between these two scenarios, there is an abrupt transition, which is interesting to study, and it leads to the definition of some scaling effects and critical phenomena, which is the stuff that we statistical physicists like so much. It's just for you to know. I don't know how many of you have physics background. It doesn't really matter. I can point you to this, to the Holm and Newman paper, and I can provide, of course, also more resources. But I think this is the last thing that I wanted to say. And with that, basically, we are done with the lectures. There is one last hands-on session